All right, I'm going to try to demystify the curve tracer. It's a fancy machine, and not many people will ever see one. And this one's acting up. There we go. So an oscilloscope gives you a plot of time versus amplitude. A spectrum analyzer gives you a view of frequency versus amplitude. A curve tracer gives you a graph of voltage versus current. That's right, voltage in this direction and current in that direction. And so it's basically a power supply that allows you to measure things, okay? So your power supply has a voltage meter and a current meter, right? You can measure how much voltage and how much current. Well, that's what this is how much voltage and how much current. And so voltage is going to be in this direction and current's going to be in this direction. So let's go ahead and show that. And so I'm going to put a voltmeter here in the picture, and I'm going to hook up voltmeter to the output, okay? And they're at 0 volts. And as I turn this knob, the voltage goes up. It's like turning on a power supply, right? And I have it set to 1 volt per division. So 1 volt is 1 volt. 2 volts is 2 volts. 3 is 3, right? This is 5 in the middle. And then way over here is 10, right? So 10 volts. So it's voltage in this direction, okay? And we can change the scale. I can make it 1 volt per division or 1 microvolt per division. I can make it anything I want, but it's volts in this direction. And it's amps in this direction. So let's go ahead and hook that up. So in the same situation, I'm going to put the meter on milliamps, and I'm going to hook up the ammeter. I haven't changed where the connections are. I've just changed the meter, right? And turn it on so you can see it again. And so as I turn it on, you'll say, oh, wait a minute. Oh, 1 milliamp, 2 milliamps, 3 milliamps, 4 milliamps, 5. Should be 10 milliamps up at the top. There we go, 9. Oh, I wasn't at the top. This is the top. 10, right? And so there we go. So it's a current in this direction and volts in this direction, okay? And I had it set to 1 milliamp per division, but I can set that to other things. This power supply goes up to 10 amps, right? And I could have 1 amp per division, 1 amp, 2 amps, 3 amps, all up to 10 amps. In volts, this power supply can go up to 1500. So I could go all the way to 1500 volts on this thing, and everything in between, okay? So that's what it's going to be measuring, is volts and amps. All right, but just like frequency generators can output a single frequency, this has the ability to output swept voltages as well. You could have swept frequencies in a generator. Well, this can have swept volts, okay? And so, so we can do that. We can turn this knob, and we can sweep the voltage back and forth. Is that on camera? Maybe it's kind of way down there. I can move the spot up so you can watch it. So now it's drawing a line, and that line is because it's sweeping back and forth, and the phosphor of the CRT lets you see it all the time. But it's actually going back and forth 120 times a second, okay? It's rectified AC, so it's 120 hertz that it's scanning back and forth. And it's 1 volt division, so it's scanning back and forth, 0 volts to 1 volts, 0 volts to 5 volts, or 0 volts to 10 volts, right? All right, so let's put it back down here. What if I put a wire? I'm going to short the machine out, okay? I'm going to put a wire directly across the inputs, and so it's a dead short. And then as I turn it on, the current will go up, and I can set it to sweep between 0 current and 5 milliamps, 0 to 5 milliamps, or 0 to 10 milliamps, right? It's sweeping because it's seeing a dead short, so it's only sweeping as far as I'm allowing it to sweep, okay? All right, so that's the way that works. Now, what if I put in a resistor, okay? So let's put in the resistor, and you can see what it looks like, and then I'll explain why it looks the way it looks like. Well, it looks like a straight line. Why? Well, because remember, voltage equals current times resistance, okay? And so we're going to measure volts, and we're going to measure current at the same time. This is how many volts, and this is how much current. And a resistor, then is volts divided by current. Volts divided by current is a ratio, and rise over run is a ratio, right? It's a slope. And this slope is exactly what a 1,000 ohm resistor would do, right? If I have 1 volt per division, so I have 10 volts here, and I have 1 milliamp per division, I have 10 milliamps. So 1 volts, 10 milliamps. If you do the equation, all right, if you take 1 milliamp and you multiply it by 1,000 ohms, you get 10 volts, right? I'm sorry, 10 milliamps. If we go right here, it's 1 milliamp and 1 volt. 1 milliamp and 1 volt is what happens when you have a 1K resistor. Okay, so maybe that was a better way to explain it. All right, so that's resistors will always plot along a straight line. Something with more resistance will be tilted one way, and something with less resistance will be tilted another way, but it'll be a straight line. Okay, so there we go. We have volts and amps, and that's really all you need to know. So we can put something in like a diode. Okay, put it in the right way around. It helps. Okay, there we go. What happened? What just happened? Okay, I'm at 1 volt per division, and suddenly it turns on. Well, that's because a diode, after about 0.7 volts, starts to turn on. It starts to conduct. Well, we can take a look at that better. We can change the horizontal scale of our machine. Okay, and now we see this curve. Well, that's a diode curve. Is so many milliamps is so much current, right? The higher the voltage, the more and more you turn on, the more and more you're able to pass through the diode, okay? And so this diode right here, okay, 100 millivolts, so it's 1, 2, 3, 4, 5, almost 0.6 volts to get to 10 milliamps, okay? 10 milliamps is at the top because we're 1 milliamp per division. So that's what a diode does, okay? So diode has a curve here. And that diode had about a 0.6 volt turn-on voltage, right? Here's another diode, and it has a much smaller voltage. It only requires maybe 0.2 volts to turn on. That's a Schottky diode. So different diodes will have different curves, right? Okay. Well, what about Zener diodes? Let's take a look at a Zener diode. I think this is a Zener diode. Let's put him in and sweep him. And oh, he looks just like a normal diode because I have him in right way around, right? And so he's about 0.77 volts turn-on voltage. It looks like a normal diode, okay? This goes up to 10 milliamps, and it's 100 millivolts per scale, so 1, 2, 3, 4, 5, 6, 7.7, about 0.77 volts at 10 milliamps, okay? But what about in the reverse direction? Zener diodes are very interested in the reverse direction, okay? Let's go in the reverse direction. We can just push a button here, and now we can go in the reverse direction. We're going backwards this time, okay? And we need to change the amount of volts that we have here. And there we go. A Zener diode also has a curve, but in the negative direction. So here's 1 volt per scale. 1 volt, 2 volts, 3 volts, 4 volts. At 10 milliamps, it's about 4.7 volts. And this is a 4.7 volt Zener. And so that's a Zener. A lot of people like to see Zeners, see the forward part and the reverse part. Well, there's a button on here to do that. You can press it here, and you can get the forward. So 0 is right in the center. It can go forward conduction and reverse conduction. So that's a Zener diode, right? Okay, and you see these in other types of tracers probably, where you can build one really, really cheap just with a transform and stuff like that. You could put things like capacitors. Let me see if I can grab a capacitor here. We'll stick a capacitor in. A capacitor is going to look like a circle. Okay, so kind of goes round and round and round. So you can do things just like you can on one of those octopus type testers and stuff. Okay. But what we're interested in is learning about transistors. Now, transistors are strange devices. Okay. All right, so I've put in a transistor, and these are the transistor curves that you might see printed in books and things like that. these are a family of curves. And so I'm going to try to explain how this works, okay? Why does it look this way? What is that? Why would an engineer care about something like that? Well, and what information does it tell me, right? And this is one transistor. If I pull this transistor out and I put in a different transistor, ooh, that transistor looks completely different. So why would I want that transistor? Or why would I want the other transistor? And again, what do these curves mean? And why does it just look so strange? Okay, a lot of people are very, very confused about what these curves are. All right. So this is the circuit that we're going to be looking at with this machine. Remember, this machine can measure current and it can measure voltage. Okay, and so it's going to measure this point here, all right? It's going to measure the voltage at this point here. It's going to measure the current through here, okay? And so it'll see how much current's going through. And so this is voltage measured. We can change all of these things. We can set the voltage we want here. We can change the resistance in the circuit. This is the transistor that we're testing, and then we can put in so much current, so much base current. Okay, so this is base current. So we can change all of these things on the machine. Okay, so the amount of voltage on that resistor, on that very, very top, remember the output? Okay, that's this knob here. Oh, can you see that? You can't see that. That's this knob here. This knob sets how much voltage is going to be on our circuit. And I'm going to set it to 10 volts, okay? So here's where 10 volts is. So I'm putting 10 volts on that resistor, and I'm getting this picture. Well, what is this picture? Well, this picture is a family of curves. Let's just do one to make it very, very simple, okay? So we're going to have just one thing here. What do you mean one thing? Let me make it bigger, okay? And so it's going to do this. What are you doing? Okay, so we are going to tell it we want to put in so much base current. And this tells us how much base current we're putting in. We're putting in 10 microamps. We're putting in 10 microamps of base current, okay? And then we're going to measure the current through the transistor. Current, remember, is the y-axis. So how much current do we have? Well, we have 500 microamps per division. So we have 1 milliamp. We have about let's see, we can make it bigger, make it easier to read. Okay, so 200. So it's 2, 4, 6, 8, 10, 12, about 12 and a half hundred microamps. So about 1.2 milliamps. We're putting in 10 microamps and we're getting out 1.2 milliamps. Okay. That is the beta of the transistor. Remember, transistors multiply gain. You put in a little bit of current and you end up getting a lot of current out. And the ratio of how much output current you have to how much input current you have, that is the beta of a transistor, okay? And right here it tells us that we can also read the beta right off of the vertical thing. It's 20, beta of 20 per division. So 2, 4, 6, 8, 10, 12, okay? That's 120. It's about 130, beta of 130, okay? And so you can read the beta directly off of the machine here. I hope that made sense. You're putting in a little bit of current and you're getting a lot of current out. But why is there a curve? Why is this curve here? Well, that's because the transistor doesn't work very good at small voltages. You need to have enough voltage to make it work. And then once you have enough voltage to make it work, it's always about the same, okay? But how come it doesn't go all the way across? Well, that has to do with the resistor that we're using, okay? Remember I said that you could choose the voltage and choose other things. So we chose 10 volts here, and we chose 10 microamps here, okay? We're measuring about, what did I say, 1200 microamps here. Okay, so 10 in, 1200 out. That's a beta of 1200 divided by 10. That's a beta of 20, HFE of 120. And so that's the gain of our system. But what resistor do we have? Well, that we can set on the machine. Right now, it's set on 650, okay? And so right now we have 650 ohms right here, right? Meter just beeped at me. 650 ohms. So remember, we have voltage equals I times R, right? We have 1.2 milliamps. That's our 1200 microamps. 1 milliamps. We have 650 ohms, okay, which is 650, 1.2 milli. That's about 0.78 volts. Okay, what is 0.78 volts? That's how much voltage drop we have here. So it can't go to 10 volts because it's dropping some voltage here. And so our V measure is going to be 10 minus 0.78. So it's going to be about 9 and a little bit, okay? 9 and a little bit. Yeah, about 9 volts, right? It's about 9 volts. Because there's some other voltages in there and stuff too, but and that's why we're not going across all the way. So it would go to 10 volts, but we're going to drop a little bit of voltage. So that's why this doesn't go as far as this. This trace here is with the transistor off, and then this is with the transistor on. Okay, so this is 0 base current, and this is 10 microamps of base current. Well, what does 20 microamps of base current do? Okay, well, we could change that. We could change the amplitude. We can make it 20 microamps. It just went off the scale. We can bring it back down. That's 20. This is 10. There's 20. 10, 20. So more current, right? A little bit of base current, a lot of base current. More, that goes off the scale, okay? Let's turn it down. A little bit, more, okay? And so we can set it so that we have a little bit or a lot of base current, right? Well, what if we want to look at this all at the same time? Well, we can say, well, just do that for me automatically. Just go ahead and multiply. Just keep doing those, right? So it's going to have 10 microamps, then 20 microamps, then 30 microamps, then 40 microamps, then 50 microamps, okay? It's just repeating those things for us. It's called a step generator. And so this dial over here tells us how big of a steps do we take. Do we take small steps or do we take big steps? And then this tells us how many steps. You want 3 steps, 2 steps, 3 steps, 4 steps, 5 steps, 6 steps, go all the way up to 10 steps, okay? Different steps. And look at that, look at where they end up. It's like a line. Well, why is there a line? Remember, resistors give lines. We saw that resistor line here, okay? And we're getting a line this direction. Why are we getting a line that direction? Well, that's because of this resistor. If we have a little bit of current in it, we have a voltage drop. If we have more current into it, we have a bigger voltage drop. More current, bigger voltage drop. More current, bigger voltage drop. Okay, and it's linear because it's a resistor. And so here's a little bit of voltage drop, bigger voltage drop, bigger voltage drop, bigger voltage drop, bigger voltage drop. So that's why it's at a line, okay? These are the voltage drops across that resistor. It's called the load resistor, and I can change that. I can make it 140 ohms, 650 ohms, and 3K. 3K is bent way, way over, okay? And so depending on what you're measuring, you want to set this to different things. We'll leave it on 650 because it makes it look nice. Yeah, that's what you're very interested in. Now, when you're using a transistor, what are you doing? You're using it like an amplifier, and so you're changing the base current. Your input signal is changing the base current. What is changing the base current? That's these families, right? So this is a little bit of base current. This was 10 microamps, 20 microamps. So let's say you wiggle up and down for 10, 20, and 30. Let's say you're wiggling up and down here, right? So you're wiggling the base current. What happens to the output voltage? Well, the output voltage goes from that to that, right? So the output voltage is wiggling this way. It's the voltage across that resistor. And so you can kind of see that if we move this much here, we're moving this much here. Let me change it. So here, let me change this a little bit here. Okay, so in this particular instance, right, we're changing 5 microamps, okay? So this is 5 microamps, there's 10 microamps, okay? 5, 10, 20, 5, 10, 20, or 5, 10, 15, I'm sorry. 5, 10, 15, and it's wiggling up and down. Our voltage is changing quite a bit. And that's because I'm using a 3K resistor. I set it to 3K. And so you're getting a bigger voltage drop across a bigger resistance. And so depending on how much gain you want out of the system, you may want to have the output wiggle a lot, or you want to have the output wiggle just a little bit. And so this helps you kind of find that. All right, and like I said, there's a family of curves, okay? You can take a look at a lot of things all at the same time, and that helps you determine things. And you can try different voltages, you can try different currents. And you can have small signals. So these are small signals. Remember, this is only goes up to 10 volts, and it's set at 500 microamps right now. So there's 1 milliamp, 2 milliamps, 2.5 milliamps. So this one goes up to 2.5 milliamps. What if you want more than that, right? Okay, so this transistor, like I showed before, this is the other transistor was a 2N2222. This is a 2N6121. And a 6121 is a big fat package, right? And so I've set it up for more current. So now what we're doing is 50 milliamps. So 5, 10, 15, 20, 25. So 300 milliamps, right? This is 300 milliamps here. And we have our steps at 1 milliamp. So this is 1 milliamp, 2 milliamps, 3 milliamps, 4 milliamps base current. These are the different base currents. So if we wanted to use this transistor outputting a lot of power, we would need to have more base current. And we can change the amount of base current here, right? So let's put it here. Now we're at 100 milliamps per division. 1, 2, 3, 4, 5. So this is half an amp, okay? We're getting half an amp of current out of that resistor here, transistor here, right? And what collector resistor are we using? 30 ohms, okay? Here's 6.5 ohms, so 6.5 ohms. So this transistor is probably getting pretty toasty now. Yeah, it's getting kind of warm. And so you can test all sorts of things, high current things, low current things, and every transistor is unique. Some you want high currents, maybe you don't get as much beta. Small signals, maybe you'll get more amplification. So you need to choose the settings and the conditions of what you're using in your actual circuit, right? Okay, well, I don't know if that hurt or helped, but this is the circuit that we're always testing on the curve tracer. We get to choose the R, we get to choose the V, we get to choose the current coming in, and we get a picture. We hold this constant, or we make it a family of curves, okay? We can put a step in here. We can have a family of curves. We can have, say, 1 milliamp, 2 milliamps, 3 milliamps. We can step this. And this voltage sweeps back and forth, 0 to 10, 0 to 10, or 0 to 100, 0 to 1500. We can make it go back and forth, okay, this voltage here. We get to choose whatever resistor we have in order to match the circuit that we're trying to evaluate. And then we monitor the voltage. And so we get a picture of volts versus current. This is the volts that's going to be measured. And the current that's going to be measured is the current through the whole string here, okay? This is the current we measure, and that's the thing that we graph here. So we get a graph of voltage out and current through. And if we measure a transistor, it looks like this. And if we make it another base current, and another base current, and another base current, and we get a family of curves, all right? So anyway, there you go. A brief introduction to transistor curve tracers and Why you might care or why you might not care.